So we'll take a look at chapter 2 here. And chapter 2 is about a probability and the distribution. Most of you had statistics before, right? Yeah. So this is more like a review. Hopefully it'll be okay. No. So probability basically is a number, right? A numerical statement about the likelihood an event will occur. So in this book here, in many chapters we use the probability concept. So that's why chapter 2 basically is a review of the probability theory. And the probability takes a value between 1 and 0. Cannot be more than 1. Cannot be less than 0. So you cannot say I'm 120% sure, right? Because the max is 100. If it's equal to 1, this is called called a sure event. Yeah, a certain event. If it's 0, it's called impossible event. Not going to happen. And also the total for one particular event, the sum of all possible outcomes. The sum of the probabilities of all possible outcomes is equal to 1. So if I tell you the probability that you will pass this class, the probability that you will pass this class is equal to 70%, 0.7. So what's the probability you will fail in this class? 0.3. How do you know? Because there are only 2 possible outcomes. So the total has to be equal to what? 1. And 1 minus 0.7. And this is 0.3. So that's the basic rules about probabilities. So the sum of the simple probabilities for all possible outcomes of an activity must equal to 1. And how to measure probability? And how do you know if we toss a coin? So what's the probability of getting head? How do you know? There are many different ways. One approach is it's called empirical approach, or use the relative frequency approach. In other words, you can try many times. You can try 1 million times. And you probably will find, if you try 1 million times, the probability, percentage of getting, so you write down the denominator is 1 million, right? How about the top, the number of heads, yeah? And it probably will be close to 500. So this is the empirical approach, or the relative frequency approach. So in this example, historical demand for the paint is either 0, 1, 2, 3, 4 gallons per day. So you observe for the past 200 days, and then you write down, right? So there's 40 days, nobody bought anything, right? 0. And 10 days, the quantity is 4 gallons. So we have the frequency, which is the number of counts here, Total is 200. Then we can, based on the relative frequency, we can compute the probability. And the probability basically is the relative frequency. So 40 out of 200 is what? Is 20%. 80 out of 200 is 40%. But again, the total has to be equal to what? 1. So this is one approach we can use. The probability takes a value between 0 and 1, cannot be more than 1. The total is equal to 1. And the next approach, so you can do an empirical approach, so you can try many times. The second approach is it's called theoretical approach. And basically, first we take a look at what is the sample space, the number of outcomes in the sample space. Second, we take a look at the number of outcomes in a particular event. Now, what is a sample space? Sample space is a collection of all possible outcomes. So, for example, if I toss a coin, what's the sample space?
2.
No. Oh, a coin. Yeah, yes. Sorry. Is a head or tail? Yeah. Head. But how about if you roll a die?
6.
So, what's the sample space?
6.
The sample space is either 1 or 2 or 3 or 4 or 5 or 6. Yeah? But let's take a look at a particular event. What is the probability of getting the number as an even number? Let's take a look at this event. Even number.
1 out of 3.
What are the possible outcomes? 2,
4, 6.
4, 6. Yeah. Okay. How about if we roll 2 dice? What are the possible outcomes?
Of even numbers?
No. What are possible outcomes?
12.
What's the sample space?
12.
No.
1 through 6.
36. Yeah. If 2 dice, you can say the first one is 1, second is 1. First one is 1, second one is 2. First one is 1, second one is 3. First one is 1, second one is 4. First one is 1, second one is 5. Yeah. And then we can start, how about the first one is 2? So you can see this is 6 times 6. So the sample space is 36. And so the sample space is a collection of all possible outcomes. And the event is a collection of some outcomes. Have it here. So according to the theoretical approach, to figure out the probability is we take a look at the number of outcomes in the sample space, the total possible. And then we take a look at the number of outcomes in a particular event. So you take a ratio between the two. Number of outcomes in the event divided by the number of outcomes in the sample space, and that's a probability. Is that clear? You know, in this example, what's the probability of getting an even number?
1 over 6.
No, even number.
3 over 1 over 3.
The number of outcomes in the event is 3.
Yes.
The number of outcomes in the sample space is 6. So it's 1 out of 3. 3 out of 6 or 1 out of 2. Okay. Good. And the subjective approach is based on what? Based on experience. Based on experience. It's subjective. What's the possibility for the stock market to go up tomorrow? But if I ask you, if you don't follow the market, you have no idea. So this is based on experience. So now let's study the relationship between two events. And the two events are called mutually exclusive if only one of the events can occur on any one trial. So how about if we toss a coin? Two possible outcomes. Is they mutually exclusive? Either you get a head or tail, but cannot be both. Right? Cannot be both. And the same thing for if you roll a die. Either 1 or 2 or 3 or 4 or 5 or 6. Cannot have a combination of both, right? So those outcomes are mutually exclusive. Mutually exclusive. And events are said to be collectively exhaustive if the list of outcomes includes every possible outcomes. So if you roll a die, 6 outcomes. So this is collectively exhaustive.
Can you say that again, please?
So basically, we listed all the possible outcomes. So it's called collectively exhaustive. So you list all the possible outcomes. If you toss a coin, and only 2 possible outcomes, head and tail. So if you list both of them, and basically it's called collectively exhaustive. But if we study the relationship between 2 events, mutually exclusive like this. Either you take this class or you stay at home tonight. Maybe not a good example, you can take online also. But, you happy, not happy? Yes. To be, not to be? Cannot be both, right? Happy, either happy or not happy. Okay. Black and white, either black or white. But sometimes we may have, it's not a mutually exclusive. You see we have some overlapping. How about, let's say, female and taking this class. So event A is female. Event B is taking this class. So the intersection is what? Female student in this class. And how about this part? Can be a female not in this class, yes. And how about this part?
Females taking the class.
And now this part is a male student in the class. Yes. Problem. No, hold on. This is female, yeah. This is this is not taking this class. Okay, sorry. Okay. So if you have a deck of 52 playing cards. So the event A is you have a 7, yeah, draw a 7. Event B is that a heart is drawn. You have the card is a heart. But these 2 events are not mutually exclusive. Why? Because it's possible you draw a card with a 7, and the card is a heart, right? So if you draw a 7, what's the probability you get a 7 out of a deck of 52 cards? I haven't played cards for so long, I can't remember how many cards here. I used to play mahjong, yeah. 4, yeah? 4 out of 52, so that's 1 out of 13. How many hearts? 12? Or 13? Oh, yeah, yeah. To the king, yeah? To the king, okay. 13 out of 52, so 1 out of 4. But the 2 events are not mutually exclusive. It's possible you can get a a card which is 7 and a heart. Hold on. Okay. So those are the examples of mutual exclusion and also collectively exhaustive. So when you need to pay attention to 2 notation in probabilities. One is called the union. The union basically is the probability of or the intersection. The probability. So we write it as this way: A and B. Or sometimes people will say A, just AB. Or you can use this notation, yeah, the probability of A and and sometimes this is also called a joint probability. In other words, in any one trial, both events happen, right? Both events happen. And union is it's about, so this is about the probability for A and B. A union is the probability of A or B. A or B. And A or B is what? Is A or B or what? Or both. Yeah, or both. Or a notation can also write the probability of A and B. So in our previous example, so what's the probability you draw a card, the two events happen at the same time? The 7, which is event A, it's a hot event B. So it says only one card. It's a 7 and a half. 1 out of 2. What about a union? Is a 7 A or B, right? A or B. So maybe we can figure this out. 7, how many cards? 7? 4. So probably I can write is there 4 cards here? Yeah. This is a 7. And hot, how many?
1.
No, hot is 13 cards. Yes, 13 cards. This is hot. Okay. So the intersection part is 1 card, yeah. And how about this one?
4 cards.
No, the red one.
3 cards.
3 cards, yeah. And how many cards here? 12, right? This part is 12. So that's why you can see A or B is 16 out of 16 cards, not 17. If you just add these two numbers together, 4, 7, right? Cards, 13 hot cards. You add them to the 17, but you're double counting what? This one twice. But if we do separately, 3 cards here, 1 card here, and 12 cards here, the total is 16. So that's why we have this easy formula. So this is called the union rule. Yeah? So the probability for A or B is equal to the probability of A plus the probability of B minus the probability of A. Because if you A plus B, you double count this part, the intersection part. So that's why we have to minus the probability A and B. But if the two events are not mutually exclusive, then what happens to this item? They cannot happen at the same time. It's equal to 0. So for the mutually exclusive event, the probability of A or B is easy. It's equal to probability of A plus the probability of B. Okay. So you can use this formula to figure it out. And this is from a different book here. This is Titanic, the passengers. So you can see on the boat, 2,223 people. How many of them survived altogether? 700. How many of them are boys?
29.
No. Oh, I mean, how many of them are boys on this boat?
64.
Be very careful, right? 64. And how many of them are men? 1692. Okay. So if I randomly select a person, randomly select a person, what's the probability that person survived? You randomly select one person from the boat. So the denominator is what? How many? What's the sample space? How many people? 2,223. Yeah, the denominator. How many people survived? 706. Okay. So 706 divided by 2,223. How many of them are? You randomly select one person. How many are women? What's the probability that person is a woman? 422 divided by 2,223. Okay. So now let's try to find the probability of man or boy. First, let's decide whether these two events are mutually exclusive. I'm not sure what's the age cutoff, yeah? For some people, maybe 40, yeah? That's true, right? But anyway, mutually exclusive, right? Mutually exclusive. So the probability, so it's equal to what? The probability of man plus the probability of boy. What is the probability random select person? That person is a man.
1692.
1692 over 2,223. And the boy is 64. Okay? But the next one, find a man and survived. Now the two events are not mutually exclusive because it's possible a man survived. So it will be equal to the probability of man, which is 1692 divided by 223 plus the probability of survived, 706 over 223, and a minus 1. Man and survived. How many? Man and survived. Joint probability. 332 minus divided by 223. Is that clear? So the first example, mutually exclusive. So it's just the probability of man plus the probability of boy. Second one, since the two events are not mutually exclusive, so we have to subtract the probability of man and survive. Okay, good.
Can you show us how you do this one in Excel?
No. There's no need. There's no need to use Excel to solve this one. Sorry. Okay, but we have a lot more coming here. Hold on. By the way, this is just a review. Yeah. And also sometimes we have it's called a conditional probability. Now, what is a conditional probability? Conditional probability, the notation is like this. The probability of event A, and this is given. Given what? The occurrence of event B. Given the occurrence. And so if you look at the formula, how to figure out the probability of A given the occurrence of event B. So the occurrence of event B is the additional information we have. Right? So it's equal to the probability of A and B, the joint probability, divided by the probability, divided by. Or if we do some manipulation, you will find actually to figure out the joint probability A and B is equal to what? The conditional probability, the probability of A given the occurrence of event B times the probability of B. And actually, if we go back to this table, hold on, do I have an extra? Hold on. If we go to this table, can we figure out the probability of a boy given the fact that the person survived? So if you randomly select a person from the So it should be equal to what? The probability of what? Boy and survive, and divided by the probability of survive. So what's the probability of you random select a person from this boat? That person is a boy and survived.
So it's 29 over 2, 2, 2, 3.
29 divided by 2, 2, 2, 3. Yeah? And if you, the denominator, if you random select a person, that person is survived. 706 over 2, 2, 2, 3. And basically it's, if you cancel out, it's 29 over 706. And actually, if you look at the formula, it may confuse you, but if you look at it as a table, it's pretty easy. Given the fact that person is survived, how many survived? 706. So we narrow down to this row, 706. Then how many of a boy? 29. 29 out of 706. It's not that difficult. And hopefully the events, so now we're talking about, so given the occurrence of event B, so the probability of event A may change, right? The probability of, so for example, let's say event A is you get lung cancer. Event B is if you smoke. So given the fact if you smoke, so according to the data, probably the probability of getting a lung cancer will increase. So in other words, the probability of A given the occurrence of event B should not be the same as the probability of A if the two events are dependent. Randomly select a person from a population, what's the probability that person has cancer, lung cancer? Very small, let's say 0.000, hopefully as small as possible, yeah? But how about this probability? You know that person's a smoker. Now, what's the probability of getting a lung cancer? It may be 0.005. It's greater than the right side. So if that's the case, if the occurrence of event B changes the probability of A, then this is dependent events. And now what about if I give you this equation? It's an equal sign. That means what? If you toss, let's say, let me give you an example. You toss a coin, and B is the occurrence of tail in the first try. And what is the probability of getting a head in the second try? Still 50%, we know. As long as you don't use a lot of force. Yeah? So if that's the case, you can see the occurrence of event B does not changing the probability of getting a head or tail, the independent events. I have some good examples here. Hopefully income and education are dependent, right? So if you have more education, you will have more income. And this probably is independent, yeah, because it's far away. Now this dependent, independent, I don't know, sorry. Win the national, do they have to win national league and them to win? Okay, in that case, they're dependent, right? Okay. Oh, I added this slide trying to discuss the the conditional probability. But maybe we can do two more examples here. Conditional probability. The probability of someone died, but that given the fact that the person is a boy. How many boys?
29.
Or 64 boys.
64. How many died? 35. So if that's case, 35 out of what? 64. But what is the probability of you random select person, that person died? What's the probability? Died. 1,517? Divided by what?
2 to 3.
2 to 3. So now, what's the conclusion? This two event, the probability is not the same, right?
No.
So just for the fact that you're a boy, the probability of dying is different from a regular average person on a boat. These two events, because they're not the same, they're independent, dependent events.
And if they were equal, they're what?
Independent, yeah, independent. In other words, it doesn't matter if the probability is the same. So that means being the fact that you're a boy will not change in the probability you will die.
So that'll be independent.
Yeah. But probably for women, I believe the probability of dying is much. You see how many people died? 104 over what? 422. And how about if random select a person from the boat died? 17 divided by 2 to 2. So much less, smaller, yeah, much smaller. So the occurrence of the event that you are a woman, it changes the probability, significantly reduces the probability. Dependent events. Okay. And if so this is a proof, yeah. If this is the conditional probability, so it reads the probability of A given the occurrence of event B. Right? Given occurrence. If it's same as the probability of A, so this is a proof that the occurrence of event B will not change the probability. So this is the independent event. So again, maybe you needed to pay attention to this because there are a couple of questions in the quiz about this. So if they're equal, independent events. If they're not equal, dependent events. And so if that's the case, the probability of A and B is equal to the probability of A times the probability of B, which is very easy. So if you toss a coin twice, what's the probability of getting two heads? So it's the first time it's 50%, second time 50%. So the multiplication of both is 25%. And I have some interesting example here, which shows you the difference between dependent and independent. This is from a different textbook, but you draw a ball from this. I have a bag here. A bucket has 3 black balls and 7 green balls. How many balls are together? 10, right? 10 balls. Okay. You draw a ball from the bucket. Take a look at the color. You put it back. It's called sampling with replacement. Okay. Then you draw the second ball. So if that's the case, what's the probability of you draw a black ball in just one trial? 3 out of 10. Yeah, that's easy. 3 out of 10. Okay. 30%. The probability of getting 2 green balls. when we draw the first green ball, how many green balls?
7.
How many balls altogether?
10.
7 out of 10. When we draw, and then you put it back. So when we do second drawing, the fact that the first ball is green will not change the probability of a second drawing. They're independent. You know why? You always have 10 balls. So it's easy. 7 out of 10 times 7 out of 10. 49. Okay. And so the probability of black ball, how to read this? The first ball is a green ball. Yes? Given the fact the first ball is a green ball, what is the probability of getting a black ball in the second try? Yeah? The fact that first ball is a green ball, take a look at it, you put it back, what's the probability of second try is a black ball? It's same, still, it's 3 out of 10, independent. This is proof. The fact the first one is green, what's the probability the second one is green? Still 7%, independent. Is this clear? But next, dependent events. Without the replacement, you take a look at it, you throw it away. Now, when we do the first draw, what's the probability of getting a black ball? It's, probably in your handouts, that's a mistake. But I sent out for printing over the weekend, and then I proofread again. I found it's a mistake, but anyway. So the probability, but you can download a copy from my the Blackboard if you have access to Blackboard. So the probability of the 2 green balls. 2 green balls. So in this case, when you do the, well actually this shouldn't be, when we do the first drawing, what's the probability of getting a green ball? 7 out of 10. But when we do the second drawing, what's the probability of green ball? The first one's green, you throw it away. How many balls left now?
6.
9. And there's only 6 green balls left. So that's why when we do the second drawing, it's 6 out of 9. So if you do the calculation, it will be 7 out of 15. And this is the application of yes, this actually, hold on. Oh, boy. Yeah, then probably notation-wise, it should be like this. It will be better. Remember the formula? The probability of A and B is equal to the probability of A given the fact of the occurrence of B times the probability. In other words, this reads the probability for a green ball, green and green. That means when the first one is green, the second one is green. So it is equal to the probability the first one is green times the probability of second one is green given the fact the first one is green. But if you look at the number, it's very simple, right? The number. But if you look at the formula, probably it confuses.
So for
But-
the formula, you read it backwards.
But a lot of questions use your common sense. You don't have to be bothered by the formula. I guarantee you. Okay, the probability of getting a black ball draw on the second draw if the first one is green. The other one, if the first one is green, what's the probability of second one is a black ball? First one is green, you throw it away, 9 balls left. Still 3 black ball, 3 out of 9. But if you just randomly select 1 ball from this bag, what's the probability of getting a black ball? 3 out of 10. So the fact that the first one is green ball changes the probability to independent events. And this one is green, green. The first one is green. Then what's the probability? Second one is green. It is 6 out of 9, right? 6 out of 9. But if just when you do the first drawing, what's the probability of getting green ball? It's 7 out of 10. Okay. Are you still interested in statistics? Sorry. Okay. And again, let's say a bucket contains 10 balls. 4 are white and a letter. But again, I found some mistakes. Over the weekend, so your number might be set different from your handouts. 4 are white and a letter. 2 are white and a number. 3 are yellow and a letter. And 1 is yellow and a number. Are you confused now? So how many are white and a letter? 4, right? Altogether 10 balls. How many white and number? 2. How many white balls?
8.
No, 6, yes? 6. How many yellow balls?
4.
4. And how many are yellow and a letter? 3, yeah? And how many yellow and a number? 1. How many are letter? 7. How many are number is 3. And then, oh yeah, I think I changed the problem. Oh yes, this is okay, so if we take a look at don't look at it here, no need. Just look at it here. How to read this? Given the fact the ball is yellow, you look at the color yellow. So what's the probability this is a letter ball? How many yellow balls? So we narrow down how many. Let's take a look at how many yellow balls.
4 yellow balls.
4 yellow balls. So the denominator is 4. That's all. Yeah. The top and how many of them are lettered? 3. 3 out of 4. 3 out of 4. We don't need to have it. Yeah. Okay. I mean, you can verify if you want. Yeah, you can verify. And we may use, it's called a Bayes theorem to modify the probability. And this is a little bit difficult, but I'm sure you learned this before. Yes? It looks familiar? Okay, looks familiar. So we have previous estimated probabilities. Now we have some new information. Then we can basically, according to this theorem, to revise. So we can have a posterior probability. So we have the old estimates. Now we have new estimates based on the new information. That's the whole thing. But for today, this is the only difficult part. The last difficult part. One is 2 dice. Yeah? One is fair. The other one is bias. So the probability of rolling 3 on the fair is 1 out of 6, of course. But for the bias one is 60%. And actually, some people will ask me to buy this magic mahjong. The magic mahjong is they have special glasses. So if you wear the glasses, you can see through the. It's illegal, right? But somebody asked me. I said no. I don't get into trouble. So we selected one by chance, toss it and get a 3. So what's the probability that die loader was fair? And what's the probability that the loader die was the biased die was loader? So this is about the conditional probability. So if you just be patient, go through this example. So the probability of the 2 balls, you randomly select one, 50% chance. So a fair ball, get a 3, is 1 of 6. Loaded the ball, get a 3 is 60%. Okay. So now you can take a look at what is the probability of get a 3 and then a ball is a fair ball. It's the joint probability. So the fair ball is 50% of chance. And if it's a fair ball, what's the probability to get a 3? 0.166. So this is 0.083. And for the loaded ball, you get a 3, and you get a 3. It is the probability of loaded ball, which 50% times 60%. So you can see this is much higher, 0.3. Okay. So if we add them together, what's the probability of getting a 3? Either it's a loaded ball or bias is 0.383. Now, if a 3 occurs, we can also know what's the probability that a ball. You get a 3, right? So what's the probability that ball is a fair? Again, that's a conditional probability. So that's equal to the fact that you get a 3. What's the probability that ball is a fair ball? So the probability of fair and 3, which is 0.083 in the previous calculation, divided by the probability of 3. So that's 0.22. And the probability that you get a 3 that the ball is loaded is 0.3 over 0.38. And we just passed the most difficult part. So I'll go over some homework. Oh, sorry, today I have to rush a little bit because of the time constraint. But I try to cover all the material. But I mean, if you don't want to have the homework discussed, that's fine with me. But I think you would be better off to go over some homework in class. So chapter 2. One question is question 16. For question 16, how many balls are chips? 8 red. This is question 16. Red is 8. Green is 10. And white is 2. So how many balls altogether?
20.
20, yeah, 20 balls. So A, how do I ask you what's the probability to get a white ball? Too easy? 2 out of 20, yes. Or 1 of 10. B, a white chip on the first draw and a red on the second. So the probability of white, oh, is this with replacement? Or replacement? Okay. White and red. So the two events are independent, right? Because with replacement. So that's probability of white times the probability of red. Probability of white is 2 out of 20 times the probability of red is what? 8 out of 20. So you can simplify it. 4 out of 5. No. 4, yeah. Hold on. 2 out of 5 times 1 out of 10. 2 out of 50. C is what? Two green ones are being drawn. 2 green ones. The probability green and green, right? And again, they're independent events. So that's 10 out of 20 times 10 out of 20. So that's 1/4. the last one, I read a chip and, the last one is conditional probability. But in this case, the conditional probability is the same as what? Because the events are independent events. So I read a chip on the second, given that a white chip was drawn first. So we're looking at for what? The probability of a red, given the fact the first one is white. So what's the probability? The first one doesn't matter, right? Because this is a sample with replacement. You always have 20 volts. So the fact the first one is white will not change the probability.
Up on B, it'd be 1 out of 25, right?
Hold on.
Yeah,
Oh yeah, sure, definitely.
it'll be the same.
So in this case, it's the probability of red, given the fact that the first one is white. It doesn't matter. So how many red? 8 out of 20. 12. Okay. Oh, do I have the error? Still have the error? Yeah, no problem. The next question is a very difficult one. It's question 23. It's all the numbers. You don't have the answers. Maybe I should have used red pen. Okay, 23. Let me list all the information we know. So we first need to list all the information we know. So the probability of question 23, yeah? The probability is properly adjusted is 80%. And not properly adjusted is what?
90.
No, 22.
20.
22, yeah. 22. So the probability of passing, if this is properly adjusted, is 0.9. And the probability of passing, not properly adjusted, I just used NA, is 0.2. Okay, 0.2. So now we first figure out what is the probability of adjusted and pass. Yeah, adjusted and pass. So it's equal to the probability of pass, given the fact this is adjusted, times the probability of this is properly adjusted. So that's 0.9 times 0.8, 0.72, that's 0. And we can also do this calculation. How about what's the probability not properly adjusted and pass? So it's equal to the probability of passing not adjusted, not properly adjusted, times the probability of not adjusted. So which is equal to 0.2 times 0.2 not properly adjusted. 0.2 and which, hold on. What's the passing of 0.2? So that's 0.04. So lastly, we can find out if a ball is passed, right? I mean, it passed the inspection. What is the probability it is properly adjusted? Conditional probability is equal to the probability of adjust and pass divided by the probability of pass. So the probability of, and this is the probability of adjusted and pass is, we did a calculation, 0.72. And divided by, what's the probability of passing? What's the probability that passing. Passing you can have properly adjusted passing or not properly. So you need to add these two together, yeah? 0.72 plus 0.74 plus 0.72 plus 0.04.
Wait, what?
0.72 plus 0.04. So the denominator is 0.76. So the final answer is 0.947. 0.947. So that answers the question. Basically, it passes. You select a ball. That ball passes the inspection, and that ball is properly adjusted. This is the most difficult one.
Yes.
Can you explain that, the last part, the pass, the bottom part?
Well, the pass, I mean, basically the pass is, what's the probability random selected ball, that ball is a pass, right? See here, you can have pass, properly adjusted is 0.72, or pass not properly adjusted, you still can pass.
Oh.
So this to the
So you have
total.
to combine them to get
Exactly.
the probability of
Okay. This is the most difficult one. Okay. May I erase it? Or maybe, okay. The other questions are easy. Question 26. So we have two events. Dick and Sally, yeah? So the probability of Dick hits a bull's eye is 90%. How about the probability of Sally hits the bull's eye?
95%.
Is a 95%. And actually for this question, we have to make some, we have to assume that the two events are independent events. So actually when you needed to answer part B first, what's the probability that D and S will both hit the bullseye? Well, you need to answer B first. The probability of D and S. But if we're assuming they are independent events, so it will be equal to probability D times the probability of S. So that's 0.9 times 0.95. Yeah. If you have calculated. Then we go to part A. Part A is what? Either, yeah? The probability of D or S. Then remember we have the formula? It's equal to the probability of D plus the probability of S minus what? The probability of D and S. The probability of it hits the bull's eye is 90%, 0.9, plus Sally is 0.95, and minus what? Minus the answer from part B. Yeah? You have the answer.
0.855.
0. What?
855.
Yeah. Good. And the question 27 is all about the setup. It's a very important. Question 7 actually is a very simple question, but you need to how to set up the question. So in a sample of 1,000 for an entire population, 650 people are from Lake Town. The rest of people from River City. Out of sample, 19 people had some form of cancer. 13 of these people were from Lake Town. So this is more like an SAT question, right? There's a lot of information. The best way is what? Construct a table. Construct a table. Once you have the table, and then the rest is it's just a piece of cake. So let's try to construct a table. A table will have what? City is from Lake Town, or from what's the other town?
River City.
River, yeah. River Town. And people have cancer or no cancer. Yeah, no cancer. So altogether we'll have 1,000 people, right? So how many people from Lake Town?
650.
650. So we know how many people from Rivertown.
350.
350. I see. How many people out of the sample? 19 people had some form of cancer. 19. 19 people have cancer. Yes. So how many people don't have cancer? 9. What? 81. Yes.
Yeah.
Because total is 1,000. But we still need more information. So. Oh, 13. So we have 13. The people, 90 people had cancer, 13 from.
Lake Town.
So that means 6 from what? So now do we have this cell? Total is 650. Minus 13 is 6 what? My mind is not working right now. 37. Yes. And how about this one? 344. So once you have this table, the rest is easy. The rest is easy. Why? Because at events of living in Lake Town and having some sort of cancer independent. So we need to do 2 calculations. One is what's the probability of getting cancer? You randomly select a person from this boat, not this boat, those villages. How many people are together? 1,000.
1,000.
How many people have cancer? 19. Yep, 90 out of. And then let's take a look at what's the probability of getting cancer if that person is from Lake Town, right? That's a conditional probability. How many people from Lake Town?
650.
Lake Town is 650. And how many of them have cancer? 13. But if these 2 are the same, they're independent. But if they're not the same, they're dependent. Okay, let's take a 5 minutes break. Then we'll finish. The last part is easy. I mean, relatively easy. Sorry. But you got to receive the email.